Last time, I think we ended up with talking about solids and liquids, obviously. And we ended up talking about sticky solids and processing involved with sticky solids. So this dash ahead and change the topic entirely by noting that 50% of all, or excuse me, 25% of all chemical reactions are between a gas and a liquid. That's very extraordinary, large quantity of very high percent, 25%. You're always interested in large surface area. Large surface area gives you good contacting. Among the things of interest, there's power input, flow regimes, interfacial area, mass transfer, and mass transfer coefficients, which means your power input, interfacial area, mass transfer, process objectives are then accomplished, and you make profits. So literally, there is a connection between power input, which is a very strange quantity for most people, and to profits, which is not strange at all. So here's some of our process objectives right here. And the reason why for the objectives: good interfacial area, you're exposing area to transport and reaction. Gas entrainment, you're pulling a gas in from the headspace. The headspace is you have the liquid surface, and then you have the tank, and up in here is called the headspace, space in the head, so to speak. The head being the top portion. You want maybe good mixing times. Now, what's interesting about gas-liquid, you got mixing times for the liquid and mixing times for the gas. So that's not it's not as exactly clear as it might lead you to. Again, mixing times of the liquid and of the gas. You're looking for high void fractions. Primarily, you want to sell air, and so you want to fill the volume with gas bubbles. You would perhaps want a uniform distribution of bubbles. Now, why you would want that, I don't know, but I assure you there are people out there, and processes out there, that they're very much interested in uniform bubbles. Boiling, you're looking for gas evolution. Perhaps you're driving off some dissolved gases. So the resistance to mass transfer, and just generally speaking, you have this bubble. So here's a bubble. And the diffusivity, mass transfer diffusivity in liquids, is very low. So it takes a long time for material to come to the surface in comparison to how quickly it can leave the surface. Inside the bubble, of course, inside the bubble. So the bubble may be of one composition, the bubble may be of a very, the concentration in here is fairly constant across the bubble, whereas the concentration across the liquid side to the interface is quite steep. So the idea of can be quite steep. Most of the resistance to mass transfer is liquid side. You also have an interface, and that gives rise to an interface resistance, and we have impurities at the interface. So we have also bubbles who remain small, and bubbles who start out small and grow very big. Okay. So small bubble regime, basically what happens is the charge collects on the surface, and it's the same charge on the bubble on the bubbles. So when the bubbles get together, same charge repels each other. So it's very difficult for the bubbles to coalesce. So that's why the bubbles remain small, basically, remain small. As opposed to small bubble regime, there is large bubble regime where the bubbles coalesce. There is no surface charge on the bubbles, and they coalesce fairly well. So you have a bubble here, and you got another bubble here, and you got to worry about whether it's positive or negative on these surfaces. If it's all positive, they will not coalesce. You're particularly interested in the regimes and the amount of interfacial area. Okay. If we go in, bubble coalescence in part is determined by the amount of electrolyte. So, good in the liquid. Good engineering practice is to know the bubble regime you're in, whether it's small bubble or large bubble. Gas phase mixing, gas circulation, concentration differences in mass transfer, multiple impeller systems. These are all areas for research. So just as a fun thing to do, I want you to go home and pour yourself a glass of Guinness, or go to a pub and order some Guinness, see if you can get Guinness. And as they pour it, you will notice the bubbles go down. There is a significant tendency for bubbles in the Guinness beer to fall rather than to rise. So that's an observation that I want you to make. Regimes around the impeller, well, power input creates interfacial area. Now there's three major power sources. Whenever you approach a process, you got to ask, where's the work being done? What's doing the work? Where's the power input? They're very helpful here. Let's see if we can bring this thing up. Well, this is KLA, mass transfer coefficient, versus gas power. The G is gas power. That's really something very hard to come by, gas power. This is John Smith, Klaus Van Riet, and John Middleton at 1977. And they really hit it on, this is a really, what they call a home run. Anyway, so down in this region, you have very low power input. The gas-style turbine, this style turbine, very low power input. Excuse me, very low mass transfer coefficients. And this is simply from sparging, gas sparging. So the impeller is not putting in very much. Now you go into this regime and you see that agitation takes control. So you're getting 0.08 down here from gas sparging, which is not very good. 0.3 here. Okay. But up in this region, you may have 0.2, right? Or 0.4. Or way up here, 0.8. Oh, wait a minute. This is 10 to the minus. Actually, if this is 10 to the minus 2, this is 0.008. Wow, that's pretty small. And this is, since this is 10 to the minus 1, this would be 0 in here as well. So you see, gas sparging is down in here at very low mass transfer coefficients. And up here you have a reasonably large increase in mass transfer coefficients. And I don't know if you can recognize it, but the curve is leveling off. And if you look, this is for water systems, not electrolyte. For electrolyte systems, it could actually get horizontal up here. Anyway, let's see what slide we got in next. Anyway, let's go back and collect that up a bit and see what. So we have three regimes. We have gas sparging. Then we have rising gas bubbles, which we didn't mention, but gas sparge, and mechanically agitated. And to be quite honest with you, this is a dirty little secret. Many gas sparged agitated tanks exist as a bulbo column. Basically what happens is you have the impeller in there, and the gas just goes up and around the impeller and out. The impeller has no effect, or it's flooded, basically. So agitation is not used very effectively. Power inputs from sparging. The impeller can be turned off. Wow, that gets lots of people angry. I was in one big chemical company giving a lecture, and the room was divided into two factions. One faction believed that the particular process had to be run 18 hours. The impeller had to be rotated for 18 hours. The other fraction of the room said, no, half an hour. So there was quite a diverse set of opinions in there. And the reason why the 18 hours was important was the seals had a tendency to leak. So the more leakage from the seals at 18 hours than there was. And it was dangerous stuff, apparently. Anyway, from what I could tell, the impeller could be turned off after half an hour, and they weren't getting very much performance from the agitator. Anyway, if you have very poor mass transfer, right, the impeller turned off, that means you can make significant process improvements. And I like this idea, a gas barge to each impeller. That's often the wise thing to do. I mentioned earlier in one of my scale-up examples, you have an impeller, and the impeller basically was performing very well with 50% of the gas here. That's your major reactor right there. The rest of the tank was a bubble column. So if you had another impeller here and sparged to it, you sparged to both impellers, what you've done is doubled the, well, not exactly doubled, but probably you'd get 40 or 50% increase in production, maybe 60. Gas liquid processes should not be operated under flooded conditions. Multiple impellers again, right here. Mixing time should be calculated for both the gas phase and liquid phase. And of course, mass transfer is very much dependent upon interfacial area. You can think of interfacial area as a sponge. You have this sponge, and the bubbles in the sponge is very similar to the bubbles in your tank. Of course, down here, you always would like to have still an impeller on the tank bottom, not necessarily a gas dispersing impeller, but a small impeller just to keep a dead zone from happening down there. So again, we have a gas barge regime, agitated tank regime, and a choked regime. Choked regime nobody talks about. The impeller can only break bubbles down to a certain size, and the impeller can only handle so much gas. Right? Nobody talks about the choked regime, but in two-phase flow, choked regimes are very common. And let me show you the choked regime and where it's coming from. Right? It's up in here. The choked regime means KLA is not going to be increasing very much. Right? So again, you have the gas barge, you have the mechanical regime, mechanically controlled KLA regime, and then you have the choked regime. In fact, this choked regime can get so bad that actually the mass transfer coefficient can actually go down. So, impeller design, you need a horizontal disc. This will force the gas to go out to the impeller blades. Gas handling capability depends upon the impeller blade number. More blades, the better. Up to a certain limit. You want it cupped in the direction of rotation, and you want to use the Smith impeller. The reason why it's called the Smith impeller is Klaas van Riet and his students, Klaas van Riet was a PhD student of John Smith, and he has undergraduate support staff of 18 students. It's quite a gang there. And they did all kinds of things, and one of the things they did was cut a pipe in half and put it on a disc. So that's what we have here. Basically, it was a pipe that was cut in half and mounted on a disc. So when a gas bubble comes up, or gas comes up from below, hits the disc, and the impeller spreads out the gas, or disperses the gas. The bottom, there's a vortices at the bottom of these blades, right? And they collect up the gas, and then they disperse the gas. So the way I draw that is, you have a vortex here and a vortex here, and some speculate if there's not a vortex in there. But anyway, you have a vortex, and this is where the dispersion happens. These two do not meet each other. Okay, with a flat blade, like the disc style, is that it fills in, gas cavity fills in. Okay, and as a result, the dispersion goes down significantly, and this impeller gets flooded. Now, then, flooded conditions for that impeller, this one right here, is like this is the amount of gas coming in, and d cubed down here. This is called the aeration number. Okay, it's the gas coming in versus the pumping of the impeller. And what happens is this impeller becomes flooded at 0.04, right? 0.04. So a very, very small amount of gas, you essentially have very poor performance. This impeller here is supposed to go all the way up to 0.2. I'm not sure. Maybe more. Okay. Now you come along and you say, well, okay, that's fine. How can I improve things? Well, you add another set of blades, basically. The more blades you have, the better your performance, up to a certain point, obviously. Certain point, just draw that right over here. So you have 6 blades, so it may look like that, and you don't have enough impeller blades. 6. So you come along and you put on 12. Okay, and so that's an improvement. It's not going to be a double. 6 going to 12 is a double in blade number, but oftentimes blade effects in mixing is 0.4. So if I went from 6 to 12, the ratio of performance might be blade number 0.4 there. Okay. So anyway, get up here and erase all this. Now then, it's very easy to have these blades flipped. Your maintenance people or the people installing this impeller, you tell them to mount it like this. And I've told this story earlier, I think. Sorry, a little bit of repeat. They'll look and say, this just doesn't look right. It's not hydrodynamic. They'll turn it around and mount it like this. Now, this is a complete disaster, basically. Who knows exactly what happens here? If there's anything that happens there, right, it might be something here and something here. Remember, the blade's going this way. And it's like, this is what they would call loser, L-O-S-E-R, and this is a winner, okay? Yes. Anyway, let's see, did we cover that? Yes. Smith impeller and proper orientation. Gas entrainment, that's when you bring in the surface entrainment, right? That may be the objective. It's used in practice. You have a deadheaded reactor, and they use the head gas to start the reaction up. The idea of surface entrainment, you're bringing in gas from the surface. You don't sparge at the same time because they're sort of, well, let's just say, as soon as you say that something can't be done, turns out that it can be. That's the way nature tricks us. But typically, if you're trying to do surface entrainment at the same time as sparge from below, they're sort of countering effects. The way of doing surface entrainment, you have the axial flow impeller near the surface. As a splasher, you may unbaffle the top portion of the tank to full vortex. Sort of like that previous slide where I said this is the way you add solids. When you add solids, you're adding gas with your powder. Liquid surface, liquid level can be controlled. Basically, you can have the impeller sitting there, and by moving the liquid level around the agitator, you can have different levels of gas entrainment. You can spin the liquid up so it's going around and around. along the wall and let it hit a beaver baffle, and that will generate a spray, and that spray will generate surface entrainment. Again, I mentioned powder always has gas with it. Got an example for you, a very simple example. I want you to drink a cup of coffee. That's not too hard, right? And you put in a packet of that fake sugar. So you put in the fake sugar, and immediately it'll go to the bottom. But after a while, there'll be foam at the surface up here. There'll be foam, right? So up here there'll be a little bit of foam. You got to ask yourself, where did that foam come from? Well, it came from adding a sugar packet or artificial sweetener packet to your coffee, and it pulled in gas, and after a while the gas will come back out and form bubbles at the surface. Of course, then you get that ridiculous single straw, right, and try to stir your coffee. Boy, if that isn't humiliating your intelligence, I don't know what is. Obviously, anybody ought to use multiple straws to stir their coffee. Big difference. So that's, since you're doing coffee anyway, you might as well go ahead and do that experiment. Use one straw, and next time use 5 straws and see what happens. Big difference. The one straw has a very small D over T ratio. This 5 straws. First thing is the coffee doesn't know it's 5 straws. It just knows that it's a big diameter impeller. All right, you know it's 5 straws, but the process doesn't. Anyway, so 5 straws is a real great mixer as opposed to a single straw. You'll also notice that the straw is, it's a full tank impeller, much like the laminar designs. So that's some experiments I want you to do. Drink a cup of coffee. Notice the foam that appears on the surface. One of the problems we have in scaling is we don't see things, right? We don't observe things because we're hidden behind a computer program. I'll tell you. Let's do some flow simulations. I'll tell you. Flow simulations are really fantastic. Don't get me wrong. I have even done some of them. However, you should not do flow visualization. You should do, you should do flow visualization. It's what you really ought to do. Do flow visualization, whether it is with a camera or whether it is with a computer. If you want to lie, use a computer. Computer simulations. What is the old story? With 3 parameters, you can draw an elephant, and with the fourth parameter, you can make the tail wag. So with computers, you can eventually get the right answer after you've fudged. Yeah, I won't pick on it in computers anymore. Anyway, surface entrainment, not desired. Trained air has problems, measurement of inventory, flow. You think you're flowing liquid, but actually you're flowing bubbles. And liquid level control. By the way, one of the interesting things about liquid level is lots of people think there's a liquid level. And indeed, there is a liquid level. Except for the fact that when it's not a liquid level, right? It could be a foam up here. And it could be a center vortex. Those are the 2 biggies. What is the liquid level of a center vortex? And if you have foam, where's the foam end and liquid begin? So it's always interesting that liquid level, most people think it's not a problem, but it can be. In pumping, air entrainment, it could lose the prime of your pump. It's not uncommon for air entrainment to be so high that you lose your pump prime. And trained gas, or trained air in particular, has oxygen in it, and oxygen is a bad actor, and it could cause product problems. If you aerate your material, you might the performance of aerated material, it could be quite different than the performance of non-aerated material. Now then, you may wish to prevent, I like the blue better, don't you? Let's go blue. You might wish to prevent air entrainment, or surface entrainment, excuse me. So, use a surface baffle. Aha! Nobody's heard of a surface baffle. That's true. That's true. Nobody ever heard of the internet in 1970, right? We got to progress with the times here, right? Things are new. So I have pictures of significant air entrainment, and I say put a surface baffle on that thing. The surface baffle is going to be a real big pain in the neck, yeah, admittedly. But if you have significant air entrainment and it's really causing you problems, a floating surface baffle might be a good choice. I had some of my students run a quick test, and it actually works. Anyway, surface baffles you sometimes see. Maybe I should go and show you a surface baffle. Anyway, shall I? Let's see what happens here. And show, discard. We'll come back, hit here, go to my movies. I guess I want to go back, and we go to Artie Barinko. Artie Barinko, where's Artie? Here's Artie. And I'll show you a surface baffle. We'll quickly tap through here. There's a surface baffle right there. See this right in here? Let's go back. Guess it's not going back for me. This is an old-time movie, obviously. Sorry. There's the surface baffle, right? They're pumping up against the surface baffle is what they're doing. Obviously, you also have significant aeration going on here, right? So, surface baffle. Not uncommon to see those. And who talks about them? Nobody. Okay, set to prevent surface. This is where we were before. Sorry. We can have surface baffle. We can operate with filled tanks, right? If you have a tank, if there's no surface there, then there will be no air entrainment. So here you could have gas entrainment here, but up in here, it's substantially reduced. So operate with full tanks. Of course, if I have a full tank, there is no surface, and as a result, there would be no surface entrainment. The other way is to have it neck down. This is the neck down. And don't have the liquid level near the impeller. That's all. Liquid level near an impeller is basically a splasher. So you don't want to necessarily have that situation happening. Liquid-liquid contacting. We're going from gas dispersion now. First we covered solids, then we covered gas-liquid, and now we're going to cover liquid-liquid. Okay, and the important research areas in here are flow regimes, bubble breakup and coalescence, interfacial area, diameter, drop diameter, sorry, mass transfer coefficients, and of course our good friend profits. Yay, profits. We need profits. Right. Power input's not much of a variable. So you have drop breakage. Now the real serious question, just a simple question, is where does drops break? And I think I showed it to you last time. Let's escape again here and show, discard, go to here. And the simple question is, where are the drops broken or made? And if we take a look, we have a pitch blade turbine here. We have the blade sitting here. we have a series of basically oil, motor oil actually, in water. And you can see the drop breakage. My video is not performing very well, unfortunately. There you go. You can see that it spreads out in a ligament, and a ligament collapses, right? Let's go further on. Here you have a ligament coming in and literally exploding into very small drops. This is one of the ways emulsions are made. So the destructive power of the vortex is being utilized here. You take a look on the plains of Texas or Oklahoma, you have tornadoes. Tornadoes are quite the mixer, so to speak. Hurricanes, typhoons, cyclones across the world are very, very much destroying things. Anyway, let's go and catch some intermediate movies in here. Anyway, these are, oh, excuse me, let me explain here. These are taken in stereo, okay, these movies. You have one view, you have another view, right? And you wear project it, you wear funny little goggles or glasses, and you can see 3 dimensions. Anyway, so if we go and do a pitch blade turbine and gas barge a pitch blade turbine, that's completely unheard of. Who would ever gas barge a pitch blade turbine? But when you gas barge a pitch blade turbine, what you can do is identify where the vortices are, because they are vortices are low pressure regions. You got one right in here. See it in there? You have another region there. Gas goes there and collects, and what they look like are streams of popcorn on a Christmas tree, so to speak. Okay. So let's go on to here. The vortices are along the top and bottom edge of this. This is a flat blade disc style turbine, right? And you can see the vortices coming off. Here's one there. It's over here. Here's one there. I guess we got one in the same spot. But usually we have one going at the top and at the bottom. Okay. Catch something here. And this is basically no gas barging whatsoever. This is literally gas being surfaced, being pulled in from the surface. Significant aeration going on. Now then, what we did, we painted the impeller black, okay? And now we're looking at looking down on the impeller, looking at the far side of the blades. So if I look here, I have the blade sitting here. The other blade is sitting here. And you can see the gas cavity in there. And that's where the gas collects and then gets dispersed from. Here is an extended gas cavity, so to speak, and dispersion area as well. So that's kind of cool. Great. Anyway, following the whole idea is what's happening in your tank. We decided to take videos of the impeller, flat blade impeller, let's go back to that one right there. Right in here, you see the oil droplet being stretched apart. Here's the other side of it to give you somewhat of a better view. You have a high-speed jet along the center line. You have a vortex system at the top of the blade, vortex system at the bottom, along the bottom edge, top edge. And the oil droplet does not break coming across the blade. I sat there and counted these things. 90% of the time, the oil droplet goes over the blade without breakage. And then it participates in this high-speed flow, and you have your dispersion over here. So, kind of interesting. And again, you can sense how far apart you need to space your blades. This probably taking up 1/3 the volume. So this blade should have at least the volume of it. So you need the volume to form the backflow. Then you need the volume to form the front flow going over the blade. And that would be very helpful. And those two volumes might be the size of the blade, maybe, something of that order. That would be a reference. These movies were like taken in 1977, and kind of obviously showing their age, so to speak. Let's go here, see what we got here. Now this is the reverse. Okay. This is the previous movies that you've seen have a very high Reynolds number, 5 times 10 to the 5th, 5 times 10 to the 6th in Reynolds number. This, where you're about to see, is Reynolds number of about 500. So here we've taken water and dyed it yellow. So the bright quantity here is actually yellow water. The continuous phase is mineral oil. And the viscosity is such that you're around 500 in Reynolds number. And you can see a number of things here, very, very interesting. First off, you can see the ligaments being stretched out. First off, there is a vortex. There's still a vortex here. Okay. And if you look really, really closely, you have a drop down in here. This is rising against gravity. This drop is trying to fall. The water was heavier than the mineral oil, right? So this drop was being carried up by the mineral oil flow. And what it do is neck down and form very, very small, tiny droplets at its tip. So here you have a Reynolds number of 500, and you have very, very small drops being produced. That would be unheard of. And then you turn around and try to relate that very small drop size to chromatograph's microscale of turbulence. There is no turbulence here, but that doesn't prevent us from trying to use something ridiculous to describe something that was strange, really strange. Anyway, you will also notice a big glob in here. Right? Go over here. See that big glob? It just stays there. Now, it's likely to stay there for an entire century, all right? You got to realize that that little blob is telling you something. First off, it's at the wall. It's attached at the wall. This is a clear plexiglass tank. It's about 3 feet in diameter. And that's part of the water that is adhered to the wall. And it's going to stay there. It's literally going to stay there for an awful long time. What's that mean? Well, what that means is if you feed at the wall, it's likely to stay at the wall, right? You can see it here. It's still there. Anyway. Lots of people feed at the wall. It's not a good idea. Lots of people feed at the wall for static electricity reasons or other reasons. But from the point of view of mixing, and you want the material to get mixed in, you need to feed it off the wall. The static electricity problem you can handle by appropriate grounding. There it is again. See, I changed. Still sitting there. Anyway. I hope you enjoyed those movies. Again, I'll go back to the presentation now. See if we got anything else. Anyway. So when I say drop breakage controlled by a local phenomenon around the impeller, Well, it's because of the trailing vortex. It occurs as the drop flows over the blade into the trailing vortices. Does not occur in the bulk of the tank. It is not two drops. Excuse me. It is not one single drop that divides into two. It is a big drop being shattered by pressure drop into very large droplet clouds. Anyway, so these vortices are, let's see if we got everything there. Yeah. The vortices, you got one at the top, one at the bottom, and a high-speed discharge jet. Pitch blade turbine, again, you have that. Trailing vortices, much like airplanes, they have vortices coming off of them. It's a very high shear zone, right? And as a result, good breakage area. By the way, there's I guess talking about shear zones, the impeller blade has the highest shear zone. If you're on a surface, right, the surface creates the high shear zone, right? So if the high shear zone sits on the surface, and the shear rates, let's go to can be quite high. In other words, if I write that as my shear rate, it could be 2,000 times the rotational speed. So that's a very high shear rate. This is on the surface, on surfaces. On surface. Anyway, in the vortex, the shear rates are maybe 200 N. They would probably be between 100 and 300 N, but let's take 200. And so the vortices are actually very high shear zones as well. There's a lot more volume in these shear zones than along the surface of the blades, so you have a sort of a balancing going on. And then the shear rates in the bulk of the tank amount to nothing. They may be 10 rotational speed. So it gives you an idea of time scales involved, by the way. Shear rate is inverse time. So lots of fast things happen at 2,000 rotational speed. At 10 rotational speed, mañana. Nah, we do it tomorrow. Here's a picture for you, a drop going over, and dispersion occurs down here. This is taken from my movies. Okay, proceeding right along. Drop coalescence, well, occurs in the bulk of the tank. The surface charge is present in effect coalescence. Very small drops formed by bursting mechanisms due to pressure drop. These don't coalesce easily if they have a surface charge to them. The bursting mechanism, right, so you got a very large drop and then suddenly you have 100,000 small drops or a very large quantity of small drops. You've got to worry about where the surface charge went to. You may have significant surface charge dilution. Large drop at a large surface charge. Smaller drops, right, there's so many of them and so much increase in area that the charge is no longer present. You can think of these drops as fresh drops, so to speak. Maybe they'll pick up a charge later. Now, a very small drop basically behaves like a hard sphere, right? I don't know if you realize that or not. But if I have pressure drop, okay, if I take my surface tension, right, and I think the equation is 1 over r, and then there's another curvature radius, right, another r. So you have surface tension divided by radius. Now, when this radius gets very small, 10 microns, 50 microns, 2 microns, and it divides into surface tension, there's a huge pressure increase across the surface area of it, or excuse me, across the interface of a drop. So you may think drops, drops. You may think drops are, same thing for gases as well. There's a huge increase in pressure drop across, pressure increase as you cross over an area of a drop or bubbles. So inside, much higher pressure than you realize. So you basically have small drops acting, very small drops acting like hard spheres. They're not going to coalesce easily. To try to make the two drops coalesce, and then it'd be kind of difficult. Same thing with bubbles. Bubbles, very small bubbles, basically are very high density because they're a lot higher density in big bubbles. There's basically three types of bubbles. I don't know. You probably won't believe this. There's small bubbles, very tiny small bubbles, which are very high pressure inside, high density as well, again, due to pressure rise across the interface. Then you have mushroom-shaped bubbles, like this, where their backflow enters. If I have a tiny bubble, it might go into this from backside, basically. There's a toroidal vortex sitting at the bottom down there as the bubble rises. Actually, it rises like this, and it goes this way. It spirals upward, and that's the effect of this toroidal vortex shedding itself on one side, then the other side, then the other side. So you have these very tiny bubbles, and then you have mushroom-shaped bubbles. And the third type of bubble you hardly ever see, but very large bubbles are very flat. They're very flat because, first off, if they were round like this, right, they would have to withstand the hydrostatic pressure. There's a hydrostatic pressure here that has to be paid for, right? If they're flat, if the hydrostatic pressure is very high, then these bubbles remain very much pancake shaped. And what then happens is, because they're pancake shaped like this, they all break. And so these large pancake shaped bubbles, you rarely ever see them. They may form initially, but they're gone quickly. Anyway, moving right along. Average drop size, let's try this, get through some of this. Average drop size is a balance between breakup and coalescence. Well, that's one way of looking at it. Or you can look at it the fact that you should consider drop breakage to be very small drops being created around the impeller, and coalescence occurring in the bulk of the tank. So you have two competing processes going on. Right. See, if I take a look at my grinding operation, right, I had this one little grinder here. Small scale worked fine. Large scale it failed. So I got to come in with a lot more grinding discs, right? Basically, the problem with this, right, the drop breakage or the grinding was, if it was only one disc, was very small in volume. Grinding is very small in volume, and the coalescence was huge. To increase the breakage, I increase the blades, and I get good performance. By the way, breakage of a drop can be very, very similar to breakage of a particle. Can be also very similar to the breakage of a gas bubble. So, I mean, there's a lot of similarities between an object, a bubble, particle, or drop. Great similarities between those as they're being processed. Okay, looking at the interfacial area, there you go, some of the objectives and the reasons for those objectives, and this needs to be updated, perhaps a potential design. Does that go over there? No. Anyway, I want an interfacial area. I want contacting without an emulsion. Those movies I showed you, pitch blade turbine, drop breakage, those those made emulsions. Perhaps I want to use uniform drop size. Maybe I want to control drop size. I want to maybe obtain a stable emulsion. Right. One job I was working on, you had to make a 10 micron drop. 1 or 2 micron would waste material, and anything greater than 15 micron would cause quality problems and break. So I can't really tell you the job, but it's looking for 10 micron drops. So we have drop breakage is an impeller-based process. Coalescence, drop coalescence is a tank process. So drop size is controlled by the impeller power input and the volume of quiescent zones. You have mixer settlers. You have a portion where you have the thing being mixed, and then over here you have the settler, so to speak. Lab is dispersion controlled, and often you have small volumes. You often have large impellers. Tank is coalescence controlled, large quiescent regions in the plant. So you have a difference. You wind up having an LN plus 1 problem occurring. Dispersion is impeller-based, coalescence is tank volume-based. Increase the blade number. Aha! There you go. Vortices are proportional. Blade area goes up. Shear rates go up. Impeller geometry. Well, we did this. And basically, we did this for our gas dispersion operations. And the effect was 0.4, as I said earlier. I would estimate it was 0.4. We didn't get a dramatic increase. Going from 6 blades to 12 blades, we did not get a double. But we got maybe this again. I suspect the same thing would occur for liquid-liquid systems. Which is the continuous phase? Aha! It's always a mystery. Location. Location in what phase determines the continuous phase? Maybe. Well, I said probably, yeah. In other words, if I have a tank here, and I have the impeller, and the impeller is down here, and this is the A phase, and then I have the B up here, then I would suspect the continuous phase would be A. Now then, if I put the impeller up here instead of down here, I would expect the continuous phase to be, well, first off, I'd probably pull in a whole bunch of air here, and then I would disperse A into B with the air bubbles. So the question is, which impeller, remember, let's take the first situation, the B being drawn down into A. The continuous phase for the impeller is the A phase, and you're going to be dispersing B into A, sort of like my oil droplets going into the vortex. The phase which contains the vortices is a continuous phase. Different levels of homogeneity exist in liquid volumes at different scales. We already know that larger tanks do not mix the same way as smaller tanks. Although the N theta values may be constant, you must realize that, well, on scale up, N theta value cannot be kept constant, right? Or excuse me, the N theta value, the theta, the mixing time can't remain constant on scale. Let me say that one more time. Get it right this time. On scale up, the mixing time for big tanks has to go up. You're just simply not possible to mix them at the same time as small scale. So as a result, you have to, large scale tanks can't mix as quickly, and because there's a lot more heterogeneity in the larger tanks. And this is why there's a D over T ratio effect. The D represents the impeller, the T represents the tank diameter. And D over T studies should be part of any pilot plant study in liquid-liquid contacting. These effects significantly exist. Okay. Other process objectives, well, you may want to have uniform drops. Large quantities means large heterogeneity. Desired uniformity not available. If you're looking for high production, you need to go turbulent flow. Anyway, uniform drops, you want to prevent large and small drops. You want to prevent stable emulsions. You want to cause stable emulsions. And here is a uniformity emulsions trick. Form an emulsion in the desired discrete phase as the continuous phase, and then you do phase inversion. The idea here, you have a drop, and then you have another drop, and you have a third drop. What happens is this filament here, when you do the phase inversion, will break. And when it breaks, you'll have this forming a drop, this forming a drop, this forming a drop, and this forming a drop. And as a result, you have uniform drops produced that way. So the idea of spreading out liquid, in the liquid sheets between two drops and then have them break will give you an emulsion. And it says here, finer emulsion than mechanical. I don't know. Okay, let's go back. One thing here for the static mixers, right? If I take a look at a static mixer, I can't have a big drop in the static mixer. The static mixer won't permit me to have a big drop. It will break it up. So one of the advantages of a static mixer is you don't have the large drops. You may have the small drops, but you won't have the large drops. The agitated tank, remember our glob of material sticking to the wall? Now that glob of material will be there. It may still be there as we speak, 20, 30 years later. So there's a problem there. You got to realize that you use large tanks for one reason, because of different level of heterogeneity there. But at the same time, it becomes a curse. Laboratory studies should... Oh, this is going to get me in a lot of trouble. So let's hit it. Laboratory studies should duplicate pilot plant operations rather than more traditional lab methods. Laboratories should use the same impurities as the plant. They should use the plant material. Whatever the plant's going to receive in the railroad cars, they should use that material in the lab. Same impurity levels as the plant. Sure, why not? You want to often study the effects of impurities. Proper operation of the plant is the objective. Moving right along, same sort of thought here. Use the same materials and methods as used in the plant. You use those in the pilot plant. Obtain the materials from the plant, the same methods as used in the plant. Laboratory studies should duplicate the plant rather than should try to duplicate the plant. I said this pilot plant-wise, but also laboratory-wise. Both the pilot plant and the laboratory should try to duplicate what happens in the plant, at least to some degree. Same fluids, same operating procedures, same method of addition, same equipment, perhaps. Now, that may be difficult to do, but, you know, it may save you a lot of grief. Anyway, I'm going to stop here and pick it up a little bit later. But let me close this a little bit out, and we'll get the heat transfer a little bit later. Anyway, gas liquid, it's been studied a lot. Liquid solids have been studied a lot. Gas solids, not so much in my area. But then you have liquid. as well. When you go to multi-phases, like gas, liquid, and solid, all three of them there, can be quite simple or quite complex. That covers everything, doesn't it? It's just now starting to evolve. There's an awful lot of phase interactions. It can be similar to two-phase behavior, and the third or fourth phases often wind up reducing transport. When I deal with multi-phases, I would recommend thinking it this way. Suppose I had a gas, liquid, and solid. First thing I'd want to do is have an impeller on the tank bottom. And that would be primarily the solid suspension aspects of the operation. Then I would come in with my Smith impeller in the middle here, and maybe another Smith impeller here. And then I would sparge to both of those. And what would happen with this sort of operation, the bottom impeller takes care of solid suspension. These are for gas dispersion operations and would be performing quite well. And when they are performing quite well on gas dispersion, you will also get solids. The problem might be that you have a partition in here. Solids will go up here, and then the question is, will the solids then go up to here? That's a problem. Maybe you'd have a small up pumper in here somewhere, which wouldn't do much, I don't think, anyway. So important thing is to identify the dominant phase. Here the gas-liquid problem is the hardest. Solid suspension will tag along. All right. And of course, as I increase solids in gas-liquid systems, the viscosity increases, which causes a reduction in transport, reduction in heat transfer, reduction in mass transfer. So the third phase often doesn't help much. Oftentimes, or many times, the third phase has a significant effect on processing. Here's what I was talking about right here. I have solid suspension and gas sparging. I have one impeller for one process, another impeller for another process, for the other process. Heat transfer will save for another time, not at this point. One of the things I would like to point out in here that I did not is the sparger, at least from my perspective, the sparge ladder down here, is really capture, or is it being controlled by the behavior in the agitated tank. I have a colleague of mine who was very, very intelligent, very, very sophisticated, and he calculated the flow through holes in the sparge ladder, right? You calculate hole to hole, the flow coming out, gas flow coming out, and I guess liquid flow as well. If you have a liquid-liquid system or a gas-liquid system, this would apply. So he calculated a very sophisticated computer model, how to operate the process, and what sort of design you would have to have a good distribution of gas and have flow coming, equal flow coming out of each hole in the sparge ladder or the sparge ring or whatever. And basically, he then took it to the plant. Okay. And the operation probably, I could be wrong, but probably only lasted for about 15 minutes before the sparge ladder was sanded in with the solids. So he had good flow with simple liquid here, perhaps. But when you added in the solids, sand dunes started to form because the sparge ladder was trying to sparge gas against rising sand dunes. So it may have eventually come out to, looking down on this, you had a whole sanded in region and maybe one or two holes or three holes operating, letting this gas out. So you can do all the predictions you want, but in the reality, you have to run the operation. And whatever you think will occur, probably will have difficulty and won't necessarily happen the way you think does. Sort of like war. If you you have this great battle strategy, right? You're going to really clobber the enemy. So you start your battle, and it doesn't go your way. Same sort of thing. You may have a great processing strategy, but it may not go your way. Mike Tyson said one time, after the first punch, all things change, or the famous battle, some very, very famous quote in the military is, after the first shot is fired, all the battle plans go for naught, oftentimes. Anyway. Well, I'm going to stop here and pick it up next time. Next time we'll talk about heat transfer. I hope you have a good day. Bye-bye.